Isaac Newton, from Wikipedia, the free encyclopedia, at en.wikipedia.org. Sir Isaac Newton, FRS, 4th of January 1643 to 31st of March 1727, or Old Style, 25th of December 1642 to 20th of March 1726, was an English physicist, mathematician, astronomer, natural philosopher, alchemist, and theologian. His Philosophiae Naturalis Principia Mathematica, published in 1687, is considered to me the most influential book in the history of science. In this work Newton described universal gravitation and the three laws of motion, laying the groundwork for classical mechanics, which dominated the scientific view of the physical universe for the next 3 centuries, and is the basis for modern engineering. Newton showed that the motions of objects on the earth and of celestial bodies are governed by the same set of natural laws, by demonstrating the consistency between Kepler's laws of planetary motion and his theory of gravitation, thus removing the last doubts about heliocentrism and advancing the scientific revolution. In mechanics, Newton enunciated the principles of conservation of momentum and angular momentum. In optics, he invented the reflecting telescope and developed a theory of colour based on the observation that a prism decomposes white light into a visible spectrum. He also formulated an empirical law of cooling and studied the speed of sound. In mathematics, Newton shares the credit with Gottfried Leibniz for the development of calculus. He also demonstrated the generalized binomial theorem, developed the so-called Newton's method for approximating the zeros of a function, and contributed to the study of power series. In a 2005 poll of the Royal Society asking who had the greater effect on the history of science, Newton was deemed much more influential than Albert Einstein. Contents. Section 1. Biography, including 1.1 Early Years, 1.2 Middle Years, including Mathematics, Optics, and Mechanics and Gravitation, and 1.3 Later Life. Section 2. Religious views, including Newton's effect on religious thought and views of the end of the world. Section 3. Newton and the counterfeiters. Section 4. Enlightenment philosophers. Section 5. Newton's laws of motion. Section 6. Newton's apple. Section 7. Writings by Newton. And Section 8. Fame. Sections 9 see also 10 footnotes and references, 11 resources including references and further reading, and 12 external links will not form a part of this recording. Section 1. Biography. Section 1.1. Early Years. See also main article Isaac Newton's early life and achievements. Isaac Newton was born on 4th of January 1643 at Woolsthorpe Manor in Woolsthorpe by Colsterworth, a hamlet in the county of Lincolnshire. At the time of Newton's birth, England had not adopted the latest papal calendar, and therefore his date of birth was recorded as Christmas Day, 25th of December 1642. Newton was born 3 months after the death of his father. Born prematurely, he was a small child. His mother, Hannah Ayscough, reportedly said that he could have fit inside a quart mug. When Newton was 3, his mother remarried, and went to live with her new husband, the Reverend Barnabas Smith, leaving her son in the care of his maternal grandmother, Marjorie Ayscough. The young Isaac disliked his stepfather and held some enmity towards his mother for marrying him, as revealed by this entry in a list of sins committed up to the age of 19. Threatening my father and mother Smith to burn them and the house over them. According to E. T. Bell and H. Eves, Newton began his schooling in the village schools and was later sent to the King's School Grantham, where he became the top student in the school. At King's, he lodged with the local apothecary William Clark, and eventually became engaged to the apothecary's stepdaughter, Anne Storer, before he went off to the University of Cambridge at the age of 19. As Newton became engrossed in his studies, the romance cooled and Miss Storer married someone else. It is said he kept a warm memory of this love, but Newton had no other recorded sweethearts, and never married. There are rumours that he remained a virgin. However, Bell and Eves' sources for this claim, William Stukeley and Mrs. Vizant, the former Miss Storer, actually named Catherine, not Anne, merely say that Newton entertained a passion for Storer while he lodged at the Clark house. From the age of about 12 until he was 17, Newton was educated at the King's School, Grantham, where his signature can still be seen upon a library windowsill. He was removed from school, and by October 1659 he was to be found at Woolsthorpe by Colsterworth, where his mother, widowed by now for a second time, attempted to make a farmer of him. He was, by later reports of his contemporaries, thoroughly unhappy with the work. It appears to have been Henry Stokes, master at the King's School, who persuaded his mother to send him back to school so that he might complete his education. This he did at the age of 18, achieving an admirable final report. In June 1661 he was admitted to Trinity College, Cambridge. According to John Stilwell, he entered Trinity as a sizar. At that time the college's teachings were based on those of Aristotle, but Newton preferred to read the more advanced text of modern philosophers such as Descartes and astronomers such as Copernicus, Galileo, and Kepler. In 1665 he discovered the generalized binomial theorem and began to develop a mathematical theory that would later become calculus. Soon after Newton had obtained his degree in August of 1665, the university closed down as a precaution against the Great Plague. Although he had been undistinguished as a Cambridge student, Newton's private studies at his home in Woolsthorpe over the subsequent 2 years saw the development of his theories on calculus, optics, and the law of gravitation. Section 1.2 Middle Years 1.2.1 Mathematics. Most modern historians believe that Newton and Leibniz had developed calculus independently, using their own unique notations. According to Newton's inner circle, Newton had worked out his method years before Leibniz, yet he published almost nothing about it until 1693, and did not give a full account until 1704. Meanwhile, Leibniz began publishing a full account of his methods in 1684. Moreover, Leibniz's notation and differential method were universally adopted on the continent, and after 1820 or so in the British Empire, whereas Leibniz's notebooks show the advancement of the ideas from the early stages until maturity, there is only the end product in Newton's known notes. Newton claimed that he had been reluctant to publish his calculus because he feared being mocked for it. Newton had a very close relationship with Swiss mathematician Nicolas Fatio de Douillet, who from the beginning was impressed by Newton's gravitational theory. In 1691 Douillet planned to prepare a new version of Newton's Philosophiae Naturalis Principia Mathematica, but never finished it. Some of Newton's biographers have suggested that the relationship may have been romantic. However, in 1694 the relationship between the two men cooled down. At the time, Douillet had also exchanged several letters with Leibniz. Starting in 1699, other members of the Royal Society, of which Newton was a member, accused Leibniz of plagiarism, and the dispute broke out in full force in 1711. Newton's Royal Society proclaimed in a study that it was Newton who was the true discoverer, and labelled Leibniz a fraud. This study was cast into doubt when it was later found that Newton himself wrote the study's concluding remarks on Leibniz. Thus began the bitter Newton versus Leibniz calculus controversy, which marred the lives of both Newton and Leibniz until the latter's death in 1716. Newton is generally credited with the generalized binomial theorem, valid for any exponent. He discovered Newton's identities, Newton's method, classified cubic plane curves, polynomials of degree 3 in 2 variables, made substantial contributions to the theory of finite differences, and was the first to use fractional indices and to employ coordinate geometry to derive solutions to Diophantine equations. He approximated partial sums of the harmonic series by logarithms, a precursor to Euler's summation formula, and was the first to use power series with confidence and to revert power series. He also discovered a new formula for calculating pi. He was elected to Lucasian Professor of Mathematics in 1669. In that day, any fellow of Cambridge or Oxford had to be an ordained Anglican priest. However, the terms of the Lucasian professorship required that the holder not be active in the church, presumably so as to have more time for science. Newton argued that this should exempt him from the ordination requirement, and Charles II, whose permission was needed, accepted this argument. Thus a conflict between Newton's religious views and Anglican orthodoxy was averted. Section 1.2.2 Optics. From 1670 to 1672, Newton lectured on optics. During this period he investigated the refraction of light, demonstrating that a prism could decompose white light into a spectrum of colours, and that a lens and a second prism could recompose the multicoloured spectrum into white light. He also showed that the coloured light does not change its properties by separating out a coloured beam and shining it on various objects. Newton noted that regardless of whether it was reflected or scattered or transmitted, it stayed the same colour. Thus he observed that colour is the result of objects interacting with already coloured light rather than objects generating the colour themselves. This is known as Newton's theory of colour. From this work he concluded that any refracting telescope would suffer from the dispersion of light into colours, and he invented a reflecting telescope, today known as a Newtonian telescope, to bypass that problem. By grinding his own mirrors, using Newton's rings to judge the quality of the optics for his telescopes, he was able to produce a superior instrument to the refracting telescope, due primarily to the wider diameter of the mirror. In 1671 the Royal Society asked for a demonstration of his reflecting telescope. Their interest encouraged him to publish his notes on colour, which he later expanded into his Optics. When Robert Hooke criticised some of Newton's ideas, Newton was so offended that he withdrew from public debate. The two men remained enemies until Hooke's death. Newton argued that light is composed of particles or corpuscles, which were then refracted by accelerating towards the denser medium, but he had to associate them with waves to explain the diffraction of light. See Optics Book 2, Propositions 12 to 50. Later physicists instead favoured a purely wave-like explanation of light to account for diffraction. Today's quantum mechanics, photons, and the idea of wave-particle duality bear only a minor resemblance to Newton's understanding of light. In his Hypothesis of Light of 1675, Newton posited the existence of the ether to transmit forces between particles. The contact with the theosophist Henry More revived his interest in alchemy. He replaced the ether with occult forces based on hermetic ideas of attraction and repulsion between particles. John Maynard Keynes, who acquired many of Newton's writings on alchemy, stated that Newton was not the first of the age of reason, he was the last of the magicians. Newton's interest in alchemy cannot be isolated from his contributions to science. This was at a time when there was no clear distinction between alchemy and science. Had he not relied on the occult idea of action at a distance, across a vacuum, he might not have developed his theory of gravity. See also Isaac Newton's occult studies. In 1704 Newton published Optics, in which he expounded his corpuscular theory of light. He considered light to be made up of extremely subtle corpuscles, that ordinary matter was made of grosser corpuscles, and speculated that through a kind of alchemical transmutation, are not gross bodies and light convertible into one another, and may not bodies receive much of their activity from the particles of light which enter their composition? Newton also constructed a primitive form of a frictional electrostatic generator using a glass globe. See Optics, 8th query. Section 1.2.3 Mechanics and Gravitation. For further information, see Writing of Principia Mathematica. In 1677, Newton returned to his work on mechanics, i.e., gravitation and its effect on the orbits of planets, with reference to Kepler's laws of planetary motion, and consulting with Hooke and Flamsteed on the subject. He published his results in De Motu Corporum in Gyrum, 1684. This contained the beginnings of the laws of motion that would inform the Principia. The Philosophiae Naturalis Principia Mathematica, now known as the Principia, was published on 5th of July 1687 with encouragement and financial help from Edmund Halley. In this work Newton stated the three universal laws of motion that were not to be improved upon for more than 200 years. He used the Latin word gravitas, weight, for the effects that would become known as gravity, and defined the law of universal gravitation. In the same work he presented the first analytical determination, based on Boyle's law, of the speed of sound in air. Newton's postulate of an invisible force able to act over vast distances led to him being criticised for introducing occult agencies into science. With the Principia, Newton became internationally recognized. He acquired a circle of admirers, including the Swiss-born mathematician Nicolas Fatio de Douillet, with whom he formed an intense relationship that lasted until 1693. The end of this friendship led Newton to a nervous breakdown. Section 1.3 Later Life. See also the main article, Isaac Newton's Later Life. In the 1690s, Newton wrote a number of religious tracts dealing with the literal interpretation of the Bible. Henry More's belief in the universe and rejection of Cartesian dualism may have influenced Newton's religious ideas. A manuscript he sent to John Locke in which he disputed the existence of the Trinity was never published. Later works, The Chronology of Ancient Kingdoms Amended in 1728, and Observations upon the Prophecies of Daniel and the Apocalypse of St. John in 1733, were published after his death. He also devoted a great deal of time to alchemy. Newton was also a member of the Parliament of England from 1689 to 1690 and in 1701, but his only recorded comments were to complain about a cold draught in the chamber and request that the window be closed. Newton moved into London to take up the post of Warden of the Royal Mint in 1696, a position that he had obtained through the patronage of Charles Montague, 1st Earl of Halifax, then Chancellor of the Exchequer. He took charge of England's great recoining, somewhat treading on the toes of Master Lucas, and securing the job of Deputy Controller of the Chester branch for Edmund Halley. Newton became perhaps the best-known Master of the Mint upon Lucas's death in 1699, a position Newton held until his death. These appointments were intended as sinecures, but Newton took them seriously, retiring from his Cambridge duties in 1701, and exercising his power to reform the currency and punish clippers and counterfeiters. As Master of the Mint in 1717, Newton unofficially moved the pound sterling from the silver standard to the gold standard by creating a relationship between gold coins and the silver penny in the Law of Queen Anne. These were all great reforms at the time, adding considerably to the wealth and stability of England. It was his work at the Mint, rather than his earlier contributions to science, that earned him a knighthood from Queen Anne in 1705. Newton was made President of the Royal Society in 1703 and an associate of the French Académie des Sciences. In his position at the Royal Society, Newton made an enemy of John Flamsteed, the Astronomer Royal, by prematurely publishing Flamsteed's star catalogue, which Newton had used in his studies. Newton died in London on the 31st of March 1727, Old Style 20th of March 1726, and was buried in Westminster Abbey. His half-niece, Catherine Barton Conduit, served as his hostess in social affairs at his house on Jermyn Street in London. He was her very loving uncle, according to his letter to her when she was recovering from smallpox. Although Newton, who had no children, had divested much of his estate onto relatives in his last years, he actually died intestate. After his death, Newton's body was discovered to have had massive amounts of mercury in it, probably resulting from his alchemical pursuits. Mercury poisoning could explain Newton's eccentricity in late life. Section 2. Religious Views. Also see the main article, Isaac Newton's Religious Views. Historian Stephen D. Snowbellen says of Newton, Isaac Newton was a heretic, but like Nicodemus, a secret disciple of Jesus, he never made a public declaration of his private faith, which the orthodox would have deemed extremely radical. He hid his faith so well that scholars are still unravelling his personal beliefs. Snowbellen concludes that Newton was at least a Socinian sympathizer. He owned and had thoroughly read at least 8 Socinian books, possibly an Arian and almost certainly an anti-Trinitarian. In an age notable for its religious intolerance, there are few public expressions of Newton's radical views, most notably his refusal to take holy orders and his refusal on his deathbed to take the sacrament when it was offered to him. In a view disputed by Snowbellen, T.C. Fitzenmeyer argues that Newton held the Eastern Orthodox view of the Trinity rather than the Western one held by Roman Catholics, Anglicans, and most Protestants. In his own day, he was also accused of being a Rosicrucian, as were many in the Royal Society and in the court of Charles II. Although the laws of motion and universal gravitation became Newton's best-known discoveries, he warned against using them to view the universe as a mere machine, as if akin to a great clock. He said, "Gravity explains the motions of the planets, but it cannot explain who set the planets in motion. God governs all things and knows all that is or can be done." His scientific fame notwithstanding, Newton's studies of the Bible and of the early Church Fathers were also noteworthy. Newton wrote works on textual criticism, most notably an historical account of two notable corruptions of Scripture. He also placed the crucifixion of Jesus Christ at 3rd of April AD 33, which agrees with one traditionally accepted date. He also attempted, unsuccessfully, to find hidden messages within the Bible. See also Bible Code. In his own lifetime, Newton wrote more on religion than he did on natural science. He believed in a rationally immanent world, but he rejected the hylozoism implicit in Leibniz and Baruch Spinoza. Thus he ordered and dynamically informed universe could be understood, and must be understood by an active reason, but this universe, to be perfect and ordained, had to be regular. Section 2.1. Newton's effect on religious thought. Newton and Robert Boyle's mechanical philosophy was promoted by rationalist pamphleteers as a viable alternative to the pantheists and enthusiasts, and was accepted hesitantly by orthodox preachers as well as dissident preachers like the latitudinarians. Thus the clarity and simplicity of science was seen as a way to combat the emotional and metaphysical superlatives of both superstitious enthusiasm and the threat of atheism, and, at the time, the second wave of English deists used Newton's discoveries to demonstrate the possibility of a natural religion. The attacks made against pre-Enlightenment magical thinking and the mystical elements of Christianity were given their foundation with Boyle's mechanical conception of the universe. Newton gave Boyle's ideas their completion through mathematical proofs and, perhaps more importantly, was very successful in popularizing them. Newton refashioned the world governed by an interventionist God into a world crafted by a God that designs along rational and universal principles. These principles were available for all people to discover, allowed people to pursue their own aims fruitfully in this life, not the next, and to perfect themselves with their own rational powers. Newton saw God as the master creator, whose existence could not be denied in the face of the grandeur of all creation. But the unforeseen theological consequence of his conception of God, as Leibniz pointed out, was that God was now entirely removed from the world's affairs, since the need for intervention would only evidence some imperfection in God's creation, something impossible for a perfect and omnipotent creator. Leibniz's theodicy cleared God from the responsibility for l'origine du mal, by making God removed from participation in his creation. The understanding of the world was now brought down to the level of simple human reason, and humans, as Odo Marquard agreed, became responsible for the correction and elimination of evil. On the other hand, latitudinarian and Newtonian ideas taken too far resulted in the millenarians, a religious faction dedicated to the concept of a mechanical universe, but finding in it the same enthusiasm and mysticism that the Enlightenment had fought so hard to extinguish. Section 2.2. Views of the End of the World. See also Isaac Newton's Occult Studies and Eschatology. In a manuscript he wrote in 1704 in which he describes his attempts to extract scientific information from the Bible, he estimated that the world would end no earlier than 2060. In predicting this he said, "This I mention not to assert when the time of the end shall be, but to put a stop to the rash conjectures of fanciful men who are frequently predicting the time of the end, and by doing so bring the sacred prophecies into discredit as often as their predictions fail." Section 3. Newton and the Counterfeiters. As Warden of the Royal Mint, Newton estimated that 20% of the coins taken in during the Great Recoinage were counterfeit. Counterfeiting was high treason, punishable by being hung, drawn and quartered. Despite this, convictions of the most flagrant criminals could be extremely difficult to achieve. However, Newton proved to be equal to the task. Disguised as an habitué of bars and taverns, he gathered much of that evidence himself. For all the barriers placed to prosecution, and separating the branches of government, English law still had ancient and formidable customs of authority. Newton was made a justice of the peace, and between June 1698 and Christmas 1699 conducted some 200 cross-examinations of witnesses, informers, and suspects. Newton won his convictions, and in February 1699 he had 10 prisoners waiting to be executed. Possibly Newton's greatest triumph as the King's attorney was against William Chaloner. One of Chaloner's schemes was to set up phony conspiracies of Catholics, and then turn in the hapless conspirators whom he entrapped. Chaloner made himself rich enough to posture as a gentleman. Petitioning Parliament, Chaloner accused the Mint of providing tools to counterfeiters, a charge also made by others. He proposed that he be allowed to inspect the Mint's processes in order to improve them. He petitioned Parliament to adopt his plans for a coinage that could not be counterfeited, while at the same time striking false coins. Newton was outraged, and went about the work to uncover anything about Chaloner. During his studies he found that Chaloner was engaging in counterfeiting. He immediately put Chaloner on trial, but Chaloner had friends in high places, and, to Newton's horror, Chaloner walked free. Newton put him on trial a second time with conclusive evidence. Chaloner was convicted of high treason and was hanged, drawn and quartered on 23rd of March 1699 at Tyburn Gallows. Section 4. Enlightenment Philosophers. Enlightenment philosophers chose a short history of scientific predecessors, Galileo, Boyle, and Newton principally, as the guides and guarantors of their applications of the singular concept of nature and natural law to every physical and social field of the day. In this respect, the lessons of history and the social structures built upon it could be discarded. It was Newton's conception of the universe based upon natural and rationally understandable laws that became the seed for Enlightenment ideology. Locke and Voltaire applied concepts of natural law to political systems advocating intrinsic rights. The physiocrats and Adam Smith applied natural conceptions of psychology and self-interest to economic systems, and the sociologists criticized the current social order for trying to fit history into natural models of progress. Monboddo and Samuel Clarke resisted elements of Newton's work, but eventually rationalized it to conform with their strong religious view of nature. Section 5. Newton's Laws of Motion. See also the main article, Newton's Laws of Motion. The famous 3 laws of motion. Newton's first law, also known as the law of inertia, states that an object at rest tends to stay at rest, and that an object in uniform motion tends to stay in uniform motion unless acted upon by a net external force. Newton's second law states that an applied force on an object equals the rate of change of its momentum with time. Mathematically, we may write that the force vector is equal to the differential of the momentum vector with respect to time. Since the momentum vector is the scalar mass multiplied by the velocity vector, we can use the product rule to rewrite this as the velocity vector multiplied by the differential of mass with respect to time, added to the mass multiplied by the velocity vector's differential with respect to time. Assuming the mass to be constant, the first term vanishes, and we may write that F equals ma, indicating that a force F applied to an object of mass m causes it to accelerate at a rate a, the acceleration, defined so that the acceleration vector is equal to the differential of the velocity vector with respect to time. This equality requires a consistent set of units for measuring mass, length, and time. One such set is the SI system, where mass is in kilograms, length in meters, and time in seconds. This leads to force being in newtons, named in his honour, and acceleration in meters per second. Newton's third law states that for every action there is an equal and opposite reaction. This leads to an apparent paradox, exemplified by a man pulling a stone along the ground with a string. The tension in the string acts equally on the man and the stone, pulling the man back and the stone forward to the same degree. Thus no net force is experienced by the man-string-stone combination, and it cannot move. The resolution depends on considering the forces acting on each body individually. The force on the stone is more than that required to overcome friction, so the stone moves, and, if the man does not move, the string becomes slack and the stone stops. But when he does move, maintaining the tension in the string, the man, string, and stone move forward together. Section 6. Newton's apple. When Newton saw an apple fall, he found, in the slight startle from his contemplation, 'tis said, for I'll not answer above ground for any sage's creed or calculation, a mode of proving that the earth turned round in a most natural whirl called gravitation, and this is the sole mortal who could grapple, since Adam, with a fall or with an apple. A popular story claims that Newton was inspired to formulate his theory of universal gravitation by the fall of an apple from a tree. Cartoons have gone further to suggest the apple actually hit Newton's head, and that its impact somehow made him aware of the force of gravity. John Conduit, Newton's assistant at the Royal Mint and husband of Newton's niece, described the event when he wrote about Newton's life. In the year 1666 he retired again from Cambridge to his mother in Lincolnshire. Whilst he was pensively meandering in a garden, it came into his thought that the power of gravity, which brought an apple from the tree to the ground, was not limited to a certain distance from earth, but that this power must extend much further than was usually thought. Why not as high as the moon, he said to himself, and if so, that must influence her motion, and perhaps retain her in her orbit, whereupon he fell a calculating what would be the effect of that supposition. The question was not whether gravity existed, but whether it extended so far from earth that it could also be the force holding the moon to its orbit. Newton showed that if the force decreased as the inverse square of the distance, one could indeed calculate the moon's orbital period, and get good agreement. He guessed the same force was responsible for other orbital motions, and hence named it universal gravitation. A contemporary writer, William Stukeley, recorded in his Memoirs of Sir Isaac Newton's life a conversation with Newton in Kensington on 15th of April 1726, in which Newton recalled, when formerly the notion of gravitation came into his mind, it was occasioned by the fall of an apple, as he sat in contemplative mood. Why should that apple always descend perpendicularly to the ground, thought he to himself? Why should it not go sideways or upwards, but constantly to the earth's centre? In similar terms, Voltaire wrote in his Essay on Epic Poetry in 1727, Sir Isaac Newton, walking in his garden, at first thought of the system of gravitation upon seeing an apple falling from a tree. These accounts are probably exaggerations of Newton's own tale about sitting by a window in his home, Woolsthorpe Manor, and watching an apple fall from a tree. Various trees are claimed to be the apple tree which Newton describes. The King's School, Grantham, claims that the tree was purchased by the school, uprooted and transported to the headmaster's garden some years later. The staff of the now National Trust-owned Woolsthorpe Manor dispute this, and claim that a tree present in their gardens is the one described by Newton. A descendant of the original tree can be seen growing outside the main gate of Trinity College, Cambridge, below the room Newton lived in when he studied there. The National Fruit Garden at Brogdale can supply grafts from their tree, which appears identical to the flower of Kent, a coarse-fleshed cooking variety. Section 7. Writings by Newton. Method of fluxions in 1671. Of nature's obvious laws and processes in vegetation, between 1671 and 75, an unpublished work on alchemy. De Mutu Corporum Ingirum in 1684. Philosophiae Naturalis Principia Mathematica in 1687. Optics in 1704. Reports as Master of the Mint, 1701–25. Arithmetica Universalis in 1707. The System of the World, Optical Lectures, The Chronology of Ancient Kingdoms, amended, and De Mundi Systemate were published posthumously in 1728. An historical account of two notable corruptions of Scripture in 1754, and Observations on Daniel and the Apocalypse of St. John in 1733. Section 8. Fame. French mathematician Joseph Louis Lagrange often said that Newton was the greatest genius who ever lived, and once added that he was also the most fortunate, for we cannot find more than once a system of the world to establish. English poet Alexander Pope was moved by Newton's accomplishments to write the famous epitaph, "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." Newton himself was rather more modest of his own achievements, famously writing in a letter to Robert Hooke in February 1676, If I have seen further, it is by standing on the shoulders of giants. Historians generally think the above quote was an attack on Hooke, who was short and hunchbacked, rather than, or in addition to, a statement of modesty. The two were in a dispute over optical discoveries at the time. The latter interpretation also fits with many of his other disputes over his discoveries, such as the question of who discovered calculus as discussed above. And then in a memoir later, I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. Sections 9 see also 10 footnotes and references, 11 resources including references and further reading, and 12 external links are not a part of this audio recording. To see these sections, visit Wikipedia at en.wikipedia.org. This recording was produced on the 30th of July 2008 by Andrew Norman. This sound file and all text in the article are licensed under the GNU Free Documentation License, available at www.gnu.org/copyleft/fdl.html.